Hey, grade 12, so we're going to look at two-body problems today. These are also sometimes called pulley system problems, okay? So this is when you'll have two objects, sometimes more, but not likely. Usually it's two objects and they'll be connected by a string. Usually they'll specify that the string is inextensible or inelastic, and also usually via a pulley system, and also they'll usually specify that the pulley system is frictionless itself. Okay, so that doesn't mean that your whole system is frictionless, it just means that the pulley is frictionless. Okay, so how to do this? Just a number of steps. First thing that you need, sometimes they will ask you to do this, sometimes they won't, but you'll need it. The first thing you need is a free body diagram for each object. Okay, then you're going to need to choose a positive direction. And note that this is not necessarily going to be the same for the two objects. So just for, as I write down the steps, I'm going to use this example as a sort of to illustrate it. So let's say we have a pulley from the ceiling. Oh my gosh, my black cookie is gone. Okay, so we've got a pulley from the ceiling and we've got two objects hanging. Okay, over that pulley. Obviously this is not looking realistic. Okay, so there's our pulley. We've got a string connecting our two objects and via a pulley. Okay, so in order to draw a free body diagram for this, let's say this was object A and that was object B. Our free body diagram for object A, it's not experiencing any horizontal forces. This force that it's experiencing due to the rope, we call that tension. So for A, it'll be experiencing a force up of tension and a force down of weight. And object B will be experiencing the same thing, hey? Tension upwards and weight downwards. Now for the second step where we have to choose a positive direction, you have to look at the overall system. So we see if, let's say block B was heavier. If block B were to go down, that means block A would go up. Okay, so here that would mean that for block B, down is positive and up is negative because B is moving down, but A is moving up, which means for A, up would be positive and down would be negative. This step is very important because it will affect your overall, all of your maths. Okay, so please make sure you pick your direction correctly. So whatever each object would be doing, if the system were allowed to move, that would be your positive direction for that specific object, and you look at each individually. Okay, step 3, and obviously make sure that you actually need to do simultaneous equations, because sometimes, like let's say they gave us the mass of B and they asked us to determine the weight, we could just say W equals mg. We don't need to go and do simultaneous equations for that. So check the question, make sure it is a question where you actually need to do a two-body problem type of solution to it for it, usually indicated by the mark allocation. So if it's roughly 6 or more marks, that's a hint that it's a two-body problem question, that you're going to have to do simultaneous equations. Not necessarily a guarantee though, it might just be a really tricky one-body question. Okay, so step 3 is to use Newton's second law for both. Okay, so you're going to write down Newton's second law for both. So here for A, I would say, or for both of them, I would say F net equals MA. And now for A, F net would expand to be tension minus weight. And for object B, it would be the other way around because weight is positive. Okay, and now here you would keep expanding until you can substitute with two unknowns. Okay, so for, you're going to keep expanding until you can sub with two unknowns. The reason two unknowns is allowed is because we have two equations. So remember, when you do simultaneous equations, the number of variables must equal the number of equations that you're dealing with. Okay, so we're going to have two equations, which means two unknowns is okay. Then step 5, you use simultaneous equations to solve. No mush. Mushy. No. Sorry, we use simultaneous equations to solve. so that's basically all there is to this. I'm going to pause you. I'll do one sort of easier example and then one slightly trickier one. As usual, pause me when you see the question and give it a go yourself first. Okay guys, so here's your example. We've got a 20 kilogram block on a horizontal surface, and then that block is connected via a string and a pulley system to block B, which is hanging vertically. Okay, we've got two questions. Question A is to determine the frictional force experienced by block A. Let me quickly put some mark allocations in here. So this would be roughly 3 marks, and then determine the acceleration of the system. This would be 3, 4, 5, 6, roughly 7 marks. Okay. So, question A, the frictional force experienced by the block. Firstly, 3 marks indicates to us probably not simultaneous equations. So we're looking at block A, we want the frictional force, and we are given the coefficient of friction, so we can just jump straight into the fact that Fk is equal to mu k times n. Now, normal force I don't know, but I can expand because I know the mass of my block. So that's mu k times. Now I'm on a horizontal surface, my applied force is parallel to the surface, so that means normal force is equal to weight. And we keep expanding. Mu k is equal to mu k times mg, and now we can substitute and solve. So that's 0,12 times 20 times 9.8. And I do need my calculator. Okay, so we've got 20 times 0.12 times 9.8. And we get a frictional force of 23,52 newtons. Okay, nice and easy. Now our second question, to determine the acceleration of the system. Now as soon as so big hints here that we're going to be needing to do Newton's second law and simultaneous equations. The first is it's a 7-mark question. The second is the fact that they're asking for acceleration. Now the only way to determine acceleration from forces currently is using Newton's second law. Okay, so we know we're going to be using Newton's second law, but the first thing we need before we can use Newton's second law is a free body diagram. So I'm going to do one for A, I'm going to split my page in half, and I'm going to do one for B. So for A is on a horizontal surface, so that means it will be experiencing a normal force and a weight, and it will now be experiencing tension because of that rope, and frictional force in the opposite direction of the tension. Then B is hanging vertically, nice and easy. It's only got tension and weight. Okay, now we're going to be using Newton's second law, so we write it down. It's worth a mark. F net equals ma. You only need to write it once, okay? Even though we're going to do it for both, I like to just sort of write it in the middle there. And now we expand. So F net for A, we're going to need a positive direction. So if I were to allow the system to move, and it were to move, we would most likely see block B dropping and block A shifting to the right. Okay? As B dropped, A would move to the right. So that means I'm going to let right be positive for A and down be positive for B. Okay, so now when we expand for A, it's going to be tension minus friction is equal to mass times acceleration, and for B it's going to be weight minus tension is equal to mass times acceleration. Now, next step is we expand until we can substitute with only 2 unknowns. So let's check. Tension, I don't know. Friction, I know. Mass, I know. Acceleration, I don't know. So for A, I already can substitute with only 2 unknowns. Okay, for B, I don't know weight, I don't know tension, and I don't know acceleration, so I need to expand B a bit. So weight, and I can expand that to mg minus t equals ma, and now I can substitute with only 2 unknowns, so let's go for it. I'm going to have tension minus, my friction is there, 23,52, equals 20A. Remember to use the mass for your specific object. So for object A, it's 20, so I put 20. For object B, mass is 40, so it's 40 times 9.8 minus T equals 40A. Okay, now we need to solve for acceleration. They've asked for acceleration, so it's up to you. You've now had lots of practice with simultaneous equations. My preferred method of doing it is whatever they ask you for, you make the other unknown the subject. So they've asked for acceleration, so I'm going to make tension the subject here. So I'm going to have tension equals 20A plus 23,52. There are obviously loads of other ways of solving this. And then on this side, I want to find A, so I'm going to make tension the subject. So I'll have 40 times 9.8 minus 40A equals T. And now we can equate them. Okay, so now I can bring this all together and say 20A plus 23,52 equals 40 times 9.8 minus 40A, and solve for A. So I'm going to bring this across. I'm going to have 60A is equal to 40 times 9.8 minus 23,52. And then from here, I think you can quote there. So we calculate that and then divide both sides by 60. So we're going to have 40 times 9.8 minus 23,52 and then divide that by 60. And we get that the acceleration of the system is 6,14 meters per second to the minus 2. Now they did not say determine the magnitude. They would. Okay, so they would never ask you to do direction and magnitude of acceleration of a system, because the system is doing two different things. It's going to the right here, but it's going down there. Okay, so we could just say acceleration is 6.14 meters per second. If they did want direction, then you could specify. You could say the acceleration of block B is 6,14 down, or the acceleration of block A is 6,14 to the right. Okay, so this was the easier of the two examples. This is more something that you would have seen in grade 11 a lot. I'm going to show you a slightly more elevated question. So yeah, so again, pause when you see the question, try it, and then unpause to check. Okay guys, so we've now got block A on a horizontal surface connected via a string and pulley system to block B, which is on an inclined plane, and block B is also experiencing an applied force up the slope. And they give us that applied force is 17 newtons. Now they've also told us that the coefficient of friction for each of our blocks is the same. That doesn't mean they're experiencing the same friction, hey? Because block B is heavier than block A, and block B is on a slope, so it'll be experiencing weight downwards as well. So remember, your friction is a function of your normal force, which is a function of the mass of your object as well as the angle of your surface. Okay, then it also says that the system is accelerating at 0.5 meters per second. Per second, eh? Okay. Now, question A, they've asked us to determine the friction being experienced by block A. Now, usually our go-to would be Fk equals mu k times normal force. And we can expand for normal force because we know the mass of the object and we're on a horizontal surface. The problem is we don't know the coefficient of friction. But we do know that the coefficient of friction is the same for both of them. And we know the acceleration of the system. So we can use Newton's second law here to help us to determine the coefficient of friction. So first off, we need a free body diagram for each. So I need a free body diagram for A and then one for B. Okay, so for A, we're on a horizontal surface. So our free body diagram's Cartesian plane is going to be normal, horizontal and vertical. And we're going to have a normal force, we're going to have weight, we're going to have tension pulling it to the right, and we're going to have friction slowing it down. Then for object B, we're on an inclined plane, which means our Cartesian plane will tilt, and we're going to have our applied force. We're also going to have, we're going to actually have three vectors going this way, eh? We're going to have the parallel component of weight. We're also going to have tension. And we're also, I don't know where I'm going to put this in. I'll just put it in the middle. We're also going to be experiencing friction. Okay. And then obviously we've got our perpendicular forces as well. So we're going to have normal force coming up like that. And we're going to have W perpendicular down like that. Okay, so we write Newton's second law. So we know that F net is equal to MA. And now we're going to expand, making sure we have a positive direction. So odds are, if this system were to move as a system, it would be moving to the right. Eh? Our applied force would be pulling this block up, which would be pulling this block to the right as well. If it were moving the other way, then this block wouldn't move. We'd see this block just dropping until it hits there and the rope would slack. Okay, so it would be sort of pointless. So let's assume that the system is moving up in that direction. If it isn't, if it turns out the system is moving down, then it just means that our positive was actually the opposite direction of motion. Okay, so it doesn't really matter if you choose the direction of motion as positive, as long as you choose that positive for this means the same thing as positive for that. Okay, so I'm going to go with to the right as positive. So for block A, moving to the right would be positive and moving to the left would be negative. For block B, moving up the hill would be positive and moving down would be negative. So if we expand for block A, we would have tension minus friction is equal to mass times acceleration. For block B, it would be F applied minus W parallel minus tension minus friction is equal to MA. Okay, now we've got to expand until we can substitute with only two unknowns. Now we know one of our unknowns is, so one of our unknowns could be the friction. But remember, when you do simultaneous equations, the idea behind it, the reason you can do simultaneous equations is because the variable in your one equation is the same as your variable in the other equation. But we've already spoken now about the fact that friction experienced by A will not be the same as friction experienced by B. What will be the same is mu k. So we will have to expand our frictions to be in terms of mu k, and then mu k can be one of the unknowns. Okay, so we'll have tension minus mu k times normal force equals ma. Here, F applied minus, we know we're not going to be able to solve, we don't have W parallel, so we might as well immediately expand for that. So that's going to be mg sine of theta minus tension minus mu k times normal force equals ma. Okay, can we substitute? We don't know tension, we don't know mu k, we don't know normal force. Okay, so immediately we know we have to keep going. We know mu k is going to be one of the unknowns. They've told us acceleration, and we know the mass, and we can expand for normal force, so we're expecting tension to be our other unknown. So we're going to keep tension and mu k as they are. Normal force for A, because I'm on a horizontal surface, that means normal force is equal to weight, which is mg. And now here we're going to expand as well. F applied, we know mg sine of theta. We can sub for all of those already. Tension is likely to be our second unknown, minus mu k. Now normal force on an inclined plane, is equal to the perpendicular weight, which is mg cos of theta. Okay, now we are at the point where we can substitute and we'll only have two unknowns. Okay, so we're going to have T minus mu k times 2 kilograms for block A times 9.8 equals 2 times our acceleration of 0.5. And this one we substitute as well. We're going to have 17 minus, that's a 3 kg block, 3 times 9.8 times sine of 20 minus T minus mu k times, 3 times 9.8 times cos of 20 equals 3 times 0.5. Okay, bit of a nightmare here. I just want to quickly check if you can still see what's going on screen. Oh, we're running out of space. Okay, I'm going to just move you down a bit. Okay, so now we check. They asked us to find friction. In order to find the friction of block A, we'll need the coefficient of friction, which means the aim here is to find the coefficient of friction. So I'm going to make the other thing, tension, the subject. So this equation will become T equals, I'm actually going to start simplifying as we go. Okay, so this becomes 1. 1 plus 9.8 times 2 is 18.6, 19.6, 19.6. So it's 19.6 times mu k. And on this side, okay. So we're going to have 17 minus 3 times 9.8 times sine of 20. Leaving that, we're subtracting this, minus 1.5. Okay, so we're going to have 5, it's 4446. Let's keep as many decimal places as we can for now so we improve our accuracy. Our tension's moved over, and our mu k, we've got 3 times 9.8 times cos of 20, which is minus 27,6270 mu k, and that's equal to tension. Okay, now we can equate the two, and I'm still worried, you can see all the way down here. Okay, so now we're going to equate the two. So I'm going to have 1 plus 19,6 mu k equals 5,4446 minus 27,6270 mu k, and we're going to solve for the coefficient of friction. Okay, and we're going to get, so it's 19,6 plus 27,6270. Okay, and then we've got this minus 1, so then we're going 4,4446 divided by that coefficient. And I get the coefficient of friction is 0,09. Okay, and now we can go and substitute that into the friction formula to find the friction experienced by A. So we can, I'm moving up here now, sorry, we're going Fk equals mu k times n, which is 0,09. Oh, wait, we've got to expand first here, sorry. So it's mu k times normal forces, mg for A because it's on a horizontal surface. So that's 0,09 times the mass of A times acceleration due to gravity. And we get 0.09 times 2 times 9.8, 1,76 newtons left. Okay, in the opposite direction of motion. Okay, so this was a slightly more trickier one, mainly just because of how many forces we had and the fact that there was an angle going on. Okay, so at the end of the day, it doesn't really matter what your scenario looks like. If you've got your free body diagrams, and if your free body diagrams are correct, then expanding for Newton's second law should be a breeze. And then you just keep expanding until you can substitute and solve your simultaneous equation. Okay, just to show you where your marks would go, because they didn't specifically ask for free body diagrams, you actually won't get marks for this. If they asked you for free body diagrams, you would get 1 mark per vector. Okay, so these 8 marks, you would get a, use the black for this, you would get a mark for Newton's second law. Okay, I won't keep track of this. You would get a mark for your initial expansion. 2, 3. Okay, you'd get a mark for substituting, you'd get a mark for solving for mu k, and then you'd get 2 marks for your final calculation here. So probably formula and answer, or substitution and answer. So that's 1, 2, 3, 4, 5, 6, 7, 8 marks. Plus, if they had asked for your free body diagrams, an additional 4 marks for this. And here you would get 1, 2, 3, 4, 5 marks. 1 mark for both of your weights being correct. Okay. Yeah, so the questions on the worksheet are quite different to this. The first few are relatively straightforward. I know there is one that's quite tricky that talks about the fact that something like 2/3 of the friction is experienced by one block and 1/3 is experienced by the other block. Then for that one, how I want you to approach it, you'll see what I'm talking about when you look at your worksheet. So they talk about the fact that 2/3 of the total friction belongs to the one object and 1/3 belongs to the other object. So what I want you to do is talk about friction total. And when you do your 2 equations for your one object, its friction, you're going to expand that to be 1/3 of the total friction. And for your other object, its friction, you'll expand to be 2/3 of your total friction. Then you can work out your total friction. And I can't remember what they actually ask. I think they might ask you for the friction of one of the objects. When you've worked out your total friction, then if they asked you for the friction of object A, you can just say, well, it's 1/3 of that. And if they asked you for the friction of object B, you can just say it's 2/3 of that. Okay, so when you get to that question where they talk about a fraction of the friction belonging to one of them and a fraction of the friction belonging to the other one, I want you to sort of approach it like this, please. Yeah, okay, so I will send this through. I'll send you through the worksheet as well, and your memos are... Oh dear, you didn't see that, what I was explaining. Sorry.
Okay, have a look at it now. So 1/3 of the total friction, 2/3 of the total friction. Okay, so yeah, I'll send this through. I'll send through your worksheet. Sorry, this is a very long video, but we are basically now done with grade 11 physics. So after this, we're gonna I'll chat to Saunders and Solly and see what we want to do next. Maybe we can do a little bit more vertical projectile motion.